Okay, thanks, Randy, and thanks everybody for tuning in today. We are going to talk about a hailstorm that impacted the Topeka CWA and actually continued on into Wichita's area and into Oklahoma as well. But we'll just be talking about the Topeka portion. Just a couple of pictures from that event here. Fortunately, that middle picture is not a picture of Jared's windshield. Glad to hear that that storm stayed south of your area and south of the office. But just here is a quick overview of the event. So we had several supercells that moved across the Topeka CWA, but there was one dominant, long-lived supercell that was on the west side of that cluster. And when I show the radar loop, you'll see a couple of new updrafts that are merging in. But there was a long swath of at least significant 2+ inch hail associated with this supercell, and then multiple instances of 4-inch hail, which we'll talk about in depth. We did, even in COVID times, have an office-supported DSS event that was impacted. And then the last thing that I will talk about is a survey that we sent out to our forecasters that were working the event to help garner some information of what happened during the event and the predictability leading up to it. So speaking of predictability, that's where we'll start out. And this is the SPC Day 2 categorical outlook issued on the 10th, so valid for the 11th. And you can see the Topeka area mostly out of the risk for severe weather, the marginal you can see across our southeast. But other than that, anticipating most of the severe weather focus to be from southeast Kansas through the Ozarks and moving into Arkansas as well. And the reason for that was that we had a forecast for a couple of clusters of storms forming in Nebraska and then moving down through eastern Kansas as an MCS overnight into the morning hours on the 11th. So this is the HER run from 12Z the day prior, and this is what was forecast to happen during the morning of the 11th. But if we look at the radar reflectivity, this is what happened in real time. So starting at 8Z, we do see that cluster of storms, several clusters actually, that developed across Nebraska. But instead of intensifying, becoming cold pool dominant, instead those storms started to move off to the east-southeast, weakened with time, and overall dissipated by 11Z. So not quite what we were anticipating, and really changed the setup for the following day, which also changed the severe weather outlook. So that was just kind of leading up to it, some of the challenges with predictability in this event. Once we did get into the next day and it became clear that that MCS did not move through, we had a pretty unmodified environment that was supportive of severe weather across the Topeka CWA. Our day 1 came out with an enhanced across our southeast, a slight, and then marginal, pretty much encompassing the rest of the forecast area. And in addition to that, 30% hail and also a hatched area for hail indicating the potential for significant hail, especially across our southeastern CWA with decreasing probabilities further to the northwest. So this is the setup as we're moving into the day of the 11th. And I'm going to use the href here to kind of show the synoptic setup, mostly because they have a nice archive of good looking graphics. But we will step through first the 500 millibar winds, and we'll start at 15Z and then move through 21Z, which really encompasses the period of time when we were dealing with severe weather in the Topeka CWA. So you can see a shortwave trough originating in Nebraska, starting to move southeast with time. And one important thing with this feature is that we do have an enhancement in the wind, so you can see 50 to 55 knots of 500 millibar flow that starts out in Nebraska and then is moving into northeastern Kansas by this afternoon. Looking at 700 millibars, you can still see that shortwave trough reflected and moving to the southeast, but winds are quite a bit weaker at this stage. You can still see some slight backing of the winds as that shortwave trough approaches, but overall pretty light flow at 700 millibars and quite a bit lighter than what we saw at 500. And then at 850, we are seeing some light southwesterly flow, but just not a lot at this level. You still see that reflection of the shortwave trough, but again, overall some pretty light flow. However, you can start to see how this would enhance your deep layer shear with the southwesterly flow at about 10 knots at 850, but that really pretty decent flow at 500, and that'll become important later for storm organization. And then the next thing we'll look at is our 2-meter dew point and our low-level winds here. So it's July. We've got a broad area of 70 to 75 dew points across the CWA. And then you can see a weak surface boundary that is up through Nebraska, stretching into western Iowa. And that'll be something that we'll continue to watch as the afternoon progresses. And one important thing to point out here is that even as you see that wind shift, even as you see that boundary move through, we still do have some pretty good moisture behind that boundary. Still seeing those 70 dew points spreading actually behind the surface boundary, and then 65 dew points up well into Nebraska. So as that front moves through, we're not looking at this huge change in density. We're not looking at this sweeping drier air, or I don't have temperatures plotted here, but not a huge change in temperature either. So we're not looking at this really significant strong boundary that's going to move through and possibly undercut updrafts or move very quickly. So a pretty good focus for convection as we move into the afternoon. And then, as you can imagine, it's hot, it's moist. So we do have some pretty high mu cape as we move into the afternoon, looking at 3,000, 4,000 joules of mu cape. And then also here you can see the max updraft helicity from the href. So you actually see that hint of perhaps some convection developing later in the afternoon, right along that instability gradient. But overall, you can see a broad area of high instability, and shear vectors are plotted as well. So what we expected based on that enhanced 500 millibar flow, we do have some pretty decent deep layer shear oriented to the northwest. And so we'll move through a couple of the cams individually, starting with the HRRR, and this is all the 12Z runs since we're pulling this out of the 12Z run of the href. So we'll start at 18Z since that's the earliest that any of the cams had any development. And you can see 18Z on the HRRR just starting to see some bubbling across north central to northeast Kansas. And that continues over the next couple of hours. And then starts to move off the boundary and dissipate with time, possibly moving into Pleasant Hills area, and then additional development occurring possibly during the late afternoon, early evening across our southeast, maybe into Wichita's area. So shows an initiation around 18Z, but not clear exactly what's going to happen with those storms as they continue to propagate off the boundary. When we look at the Nestle Wharf, we see a little bit later initiation time, possibly some bubbling as early as 20Z. And you can imagine that boundary that we were looking at is a little bit further south by 20Z. So you do see that initiation occurring just a little bit further south, almost all the way through the Topeka CWA. And by the time those storms really start to strengthen and intensify, they're almost out of our area, moving into Wichita and Springfield's areas. So a little bit later initiation, still looking for storms to develop and become intense with time, but just a little uncertain on when they'll develop and exactly where they will be at that point. And then the NAM nest is going to be pretty similar. Not a whole lot going on for the first couple of hours, maybe seeing some bubbling by mid-afternoon, about 21Z. And then eventually more robust storms developing late afternoon into the early evening and progressing southeast with time. So pretty similar between the Nestle Wharf and the NAM nest. HRRR is hinting at possibly an earlier development. And so we'll look at the href as a whole. This is going to be where the ensemble members have reflectivity higher than 40 dBz and any area where mu cape is greater than 50, just so that we're looking at the potential for thunderstorms. And this is the ensemble neighborhood probability with a radius of 20 kilometers. So starting out in the 4-hour period from 13 to 17Z, you can see there was some quick development in Wichita's area that then dissipated. So you can see that's kind of the focus here between 13 and 17Z. Then as we move on, going into the morning, early afternoon, the first hints that we see of convective initiation would be somewhere between 16 and 20Z across north central to northeast Kansas. And then those probabilities start to increase with time, but also shift southeast as that boundary shifts southeast. and becomes more probable as we move into the afternoon. So overall, based on the cams that are incorporated into the HREF, you can see that potential for convective initiation as early as maybe late morning to early afternoon, but becoming more likely as we move southeast and move further into the day. So then we'll look at satellite. This is starting at 1526 UTC. And I've highlighted the Kansas-Nebraska border here just so that you're able to orient yourself. But due to parallax error, this is probably more likely in just far northern Kansas. But already at 1530 UTC, you can see some bubbling on satellite and perhaps the hint of either the synoptic boundary or perhaps a leftover outflow boundary from the night before. And as we move forward in time, you can see that boundary becoming a little more defined, perhaps seeing some bubbling along it and a Q field developing out ahead. So this is something that we were watching in real time and also gives some hints that convective initiation may be just a little bit earlier than we were anticipating. So clear presentation of that boundary, but also starting to see perhaps some signs of instability along and ahead of that boundary. And this is just a crude surface analysis. I'm sure Bill Gargan did a better one in real time, but this is just a little PowerPoint analysis of our surface at 16Z. And you can see not a huge gradient in temperature, not really a gradient in moisture as we would expect from the HREF analysis, but you do see the wind shift and change in temperature there. With the cold front and possibly combined with some sort of outflow from the night before, stretching across northern Kansas and then into northern Missouri. Pretty much oriented west-southwest to east-northeast, especially across our area. And again, not seeing a ton of convergence along it, not seeing a huge push of those drier dew points until you get a little further into Nebraska. So could serve for a focus for convection, especially since we're seeing those Q bubbling along it. But again, not too worried about those updrafts being undercut by significant difference in density behind that surface boundary. So we'll flip to probably my favorite RGB, the day cloud phase RGB, and we'll start around 16Z to monitor the developing Q and the potential for some glaciation as these updrafts start to bubble along the boundary. And again, we're looking just a little bit further south than what the satellite might indicate, just south of the Kansas-Nebraska border. And so as we move on with time, as we start to see these yellows popping out, first starting with green, but then yellows and oranges popping out from the lighter blues, we are starting to see glaciation with some of these updrafts that are developing along that boundary. So signs that convective initiation is already occurring possibly as early as, this would be 11:20 local time. And as we move forward in time, we can see those updrafts continue to intensify. You're really not seeing that orphaning that you might expect if the environment wasn't quite there. We're really just starting to see these updrafts take off, and especially the one that is further to the west. So this is something we were monitoring in real time and really gives you a hint that if there was a cap that you were expecting, perhaps it may not be quite as strong, or just that things are starting to trend towards deep convective initiation. So a good thing to monitor in real time to tell that that event is really starting to begin across the area. So right around that time, just shortly before, the day one outlook was updated at 1651 UTC. And mainly the changes that were made was to slide the significant hail probabilities back to the northwest, possibly in response to seeing some of the bubbling that was already occurring along that surface boundary in combination with the high degree of instability and shear as well. And as we could see on that 500 millibar plot, our shear is really the strongest across northeast Kansas. So all of these likely a factor in why that significant hail probability was pulled a little bit further to the northwest with this update. And we also did release a special sounding from Topeka. This is going to be the pre-convective environment, even though storms are starting to fire up to the north. So it gives you a good picture of what the pre-storm environment looked like. Really not a cap, even though that was something that we were anticipating during the afternoon. We may see a little bit of weakness in the lapse rates right around 750 millibars and maybe again around 600, but Nothing that looks like it's really going to inhibit deep convective initiation. And then it's also important to look at the hodograph structure as well. We see some of that kind of confusion in the lowest 3 kilometers where the winds are pretty light and variable. But then as winds start to increase aloft, we start to see our full shear profile that does look supportive of supercells, and then also our right mover, which would be to the southeast, which is good news for our west-southwest to east-northeast oriented boundary. But won't be difficult for storms to move off that boundary as it tracks to the southeast with our right mover at 24 knots. So something to be aware of as we're moving into the afternoon. We don't expect these storms to train along the boundary. We probably won't see competition from new updrafts as those storms do track off. So probably going to see some isolated supercells without a lot of interference from other updrafts. So this is just a loop of radar starting at 1745 UTC and going for about 3.5 hours. And we're focusing kind of on the supercell that develops north of Westmoreland and then moves to the southeast. And that's going to be our dominant supercell throughout the entire event. I'll just let it loop a couple of times. And you can see a couple of updrafts that merge in, but overall that supercell is kind of the dominant supercell of the event, even with those mergers that occur. And some of the plots we'll look at, you'll see some transition zones when those updrafts come in. But overall, we're just kind of looking at this one supercell despite the mergers that occur as our dominant supercell that we're going to study for this event. These are the hail LSRs that we received both during and after the event. And this is just associated with that one kind of steady state supercell that tracked southeast across the area. And you can see a number of reports. There are actually a few more than this, but a lot of them were in similar locations around similar times. So I tried to eliminate duplicates and just go with the highest that we received around the same time and around the same location. So a couple of reports from this storm, and you can definitely see the couple of giant hail reports that we did receive. And it's important to remember that with hail reports, just because you're getting a lack of reports during a certain time, perhaps early in the event, maybe in the middle of the event, it doesn't necessarily mean that you have a lack of severe hail. And that's the case for sizes as well. Even if you're looking at larger sizes and then you see a drop off and you're not getting those reports anymore, it doesn't necessarily mean that you're not getting those large sizes anymore. It's just a factor of the information that you're getting at the office. And based on the hailstone project that we did in 2011 through 15, and that was published in WAF in 2017, in general, just those true hail sizes in any supercell is going to be underestimated based on the reports that you're getting in. That maximum hail swath is pretty narrow, and there's not a great chance that that's going to move over population, especially here in the Central Plains where our population density isn't real high. And because of that, you're also going to see the maximum hail size is often not captured. So even if you're getting these large hail sizes, that may not even be the largest. So we're going to look at these 4-inch hail reports because when you get that 4-inch hail report or larger, it gives you confidence that giant hail is occurring. There's no evidence to support that people are overestimating the sizes. And in fact, in all of these cases, we got measurements and photos into the office. So we have confidence that when we get those reports, this storm is capable of producing giant hail at that time. But we can't say the same thing about the other time periods. We can't say that it wasn't producing giant hail at the times when we weren't receiving reports. So we're going to kind of focus in on those 3 4+ inch hail reports because we know at those times that the storm was capable of producing giant hail. So we'll just focus in on these 3 reports that we got from this storm. The first one was at 1840 UTC. This was 3 miles north of Paxico and a measured hailstone of 1.4 inches. So radar imagery at the time that this hailstone fell, we're looking at the lowest scan, and the storm was very close to the Topeka radar. So actually had to involve the Pleasant Hill radar as well for looking at the upper levels. But just here looking at the lower levels, we can see our base reflectivity. Just north of Paxico, you can see kind of that supercell shape, a little bit difficult to pick out here at this lowest scan. Then as you look at correlation coefficient, You can see kind of what you would expect in those higher reflectivities. You're starting to see a lowered correlation coefficient, pointing to mixed hydrometeors in the presence of hail. And that shows up as well in the KDP, where you're seeing those values eliminated, where CC is too low for KDP to be displayed. But then in ZDR, not quite what you would expect. You do see a lowering kind of on the northwest side of the storm, but where you see those higher reflectivities, you're actually seeing some pretty high KDP as well. So it looks like the giant raindrops are probably dominating the signal in that area, possibly even some shedding from wet hailstones that's really starting to dominate the signal that we get there. We do see that lowered ZDR a little bit further to the west, perhaps where hail is a little more of the contribution to the signal in that area. And then looking aloft, it's a little more what you would expect. Again, this is from the Pleasant Hill radar so that we can actually look in the mid to upper levels of the storm. So good core of 60 plus dBz throughout that storm, good storm relative velocity. You can see some good mid-level rotation associated with it at the time. Looking at correlation coefficient, you can see a good three-body scatter spike coming off of the backside of the storm, as well as the presentation of the updraft just east of the Topeka radar. And then this isn't a great angle for it because we probably could have gotten a little higher in the storm, but you can start to see that storm type divergence developing as well. So overall, really robust storm, definitely rotating well and presenting itself as a well-organized supercell at the time. And looking through a cross section that we also took from the Pleasant Hill radar, you can see, again, the good core of 60 dBz, almost to 40,000 feet, and 50 dBz even higher than that, and bounded weak echo region near that updraft. So overall, a well-organized supercell, BWER, all of the things that you would expect for a significant hail producer. And then also looked at the GO16 sandwich product, which incorporates the visible and the IR. And just stepping through a couple of frames here prior to the hail production, you can see a pretty clear updraft here, robust updraft with those cloud top coolings focused on the west side of the storm. And then right around the time that the hail was produced, you can also see that thermal couplet have a good sign of a really intense updraft and a long-lived supercell. The next storm, same storm, but the next hailstone that we will look at was observed at 1855, 4 miles west of Dover. This is a storm chaser that sent us in some measurements as well as these photos. But you can see the storm's moved a little bit further to the southeast, still very close to the radar at this time. You can see those higher reflectivities west of Dover, co-located with, again, some lowering in CC, which is also apparent in KDP. But kind of similar when we're looking at ZDR, we see some of those higher values of ZDR tied with the lowered correlation coefficient and the higher reflectivity. So again, some mixed hydrometeors in there still. Dry hail is not dominating the signal there, but it may be a little further to the west where we do start to see some negative ZDR. And we also see that in the forward flank as well, further south of Dover. And then looking at something similar for the mid to upper levels, still a good 60 dBz core, still really good rotation throughout the mid levels. You can pick out that three-body scatter spike despite the new storm that's developing right over top of the radar. And then some really good storm type divergence evident here on the highest scan from EAX. And again, looking at a cross section of a nice BWER present at this time as well. So really robust supercell continuing to the southeast. And we'll also point out, even though the BWER was a lot more evident in Pleasant Hill's radar, you can actually see it on Topeka's as well. Looking at the 12.5, you see some of those reflectivity arcing around and creating this bounded echo region just southwest of Dover. And the other thing to note here is how sheared the storm actually is. You see most of the supercell is kind of to the northwest of Dover on the lowest scan and more to the south of Dover on the 12.5. So you can get an idea of how prominent that BWER was, but also how sheared the storm is with time, which is also helping in its longevity. And we pulled up GLM for this just to look at some of the trends with the updraft as they relate to lightning. And I'm also going to show this as kind of a lesson learned for me. Because of COVID, we weren't all in the office right after this event happened and wasn't able to pull some of the data, especially the satellite data, rolls off after 2 days. We weren't able to pull all of this into the West case, but fortunately there is a nice archive of GLM that's on the UMD site, and I'll have that linked at the end. It's actually possible to work that into a West case that you've already created. So I was able to do that and wanted to kind of show that and provide instructions for it if it's something that you weren't able to grab in real time but wanted to incorporate into a West case later. So we're focusing on the storm that's north of Alma, again with parallax. It's going to be a little bit norther than you would expect. But starting at 1839, you can see the flash density over a 5-minute period with a 1-minute update. And as we move towards the time of that giant hail report at 1855, you can start to see an updraft pulse where perhaps it becomes a little bit stronger about 10 to 15 minutes prior to hail production, and then weakens again. So just kind of an interesting signal to let you know that that updraft might be intensifying at the time, and then the hail fallout occurred about 10 minutes later. And then the last storm that we will look at was a 4-inch report near Waverly, and this was almost an hour later at 20:07 UTC. Starting to see a little bit more of a classic appearance, probably because it's a little further from the radar, so we're looking a little higher up in the storm, but you actually start to see that hook echo shape that you would maybe expect with a supercell. And in reflectivity, I've drawn in this little contour a little bit closer. Before it had been to kind of show you where the lowest signal to noise ratio was, but here I want to draw it in a little bit closer so you can see exactly where the updraft might have been. And at the lowest level, you can see is still those high reflectivities, but the correlation coefficient is lowered just a little bit closer to the updraft, perhaps a little bit offset from those higher values, telling you that the hail core might be a little bit closer to the updraft here. And similar with ZDR, you see a really high, and actually it's the surface level of what is a ZDR column there near the updraft, but then you start to see those lowered values right along that reflectivity gradient, again, giving you a hint that perhaps the hail core is located very close to that updraft downdraft interface. And then looking aloft, you can see again that decent 60 dB Z core still continuing up, good rotation, good storm top divergence, and then also some hints of a ZDR column, which is something that we haven't really seen throughout the earlier stages of the storm's life cycle. So something that I wanted to look at a little bit further. And it's not super impressive as far as height is concerned, but you do see it extending above the freezing level, which is about 15,000 feet. And we see a ZDR column extending up to about 20,000 feet. So looking at some of these liquid hydrometeors being lofted a little bit higher than the freezing level, possibly indicating some melting graupel that's being recirculated into hail production, possibly even some raindrops that are being shed by wet hail that's falling. So it gives you an indication that this may be a time when embryo production is occurring or hail growth is occurring with this storm. And another thing I wanted to focus on with all of these reports is where they occurred relative to the updraft. We're looking at the low-level scans here, but you can see that all of the giant hail reports occurred on the reflectivity gradient near the updraft. And this is something that we would kind of expect because as that updraft starts to loft particles outward, the heavier ones are going to fall closer to the updraft, and the lighter ones will be cast further out. But it's just something to be aware of as you're calling for hail reports, as you're looking for hail reports and matching them up to reflectivity, that a lot of times these larger sizes are going to occur very near to the updraft and into that forward flank region where the updraft is more able to settle these heavier hailstones. And this is really similar to what we saw in the Gotobo storm, which was on our hailstone project in 2011. We took all of the hail reports and put them on a representative radar image. So kind of took all of the reports that we got and related them to this one image. And you can see that a lot of the significant, which would be in red, to giant hailstones, which would be in purple and black, were falling very close to that updraft and along the forward flank. So something to just keep in mind as you're getting these reports in and as you're looking for them. These may be falling even in some lower reflectivity, kind of on the edge of that reflectivity gradient, and not necessarily in the higher reflectivity where you might be seeing more of a rain-hail mix. So since we've talked about some of the fallibilities of the reports that we're getting into the office, we'll talk about some of the radar-based sources of hail information that might be a little bit more accurate or might be a little quicker to update, especially since they are radar-based. They should be coming in every couple of minutes. So we'll investigate some of these, which are MASH, which feeds into Prob Severe, the Donovan method, and then the giant hail checklist will be the last one that I talk about. So a couple of notes about MESH. We've all looked at it, but just reminding us what goes into it. So MESH is a temperature-weighted vertical integration of reflectivity that's occurring above the melting level. So only looking at reflectivities between 40 dBz and above the melting level. And there's also a weighting function that starts at 0 below 40 dBz. So anything below 40 dBz is not going to be counted. And then anything above 50 dBz is going to be treated the same. Since you start to see me scattering when you get into these larger sizes, you can actually see reflectivity start to fluctuate. But some of the limitations of MESH, it does struggle with highly sheared storms since it is a vertical integration. It can also struggle with significant bounded weak echo regions because you would see that lowered reflectivity as you move upward in the storm. And just fundamentally, it doesn't account for the processes that result in significant or giant hail, which is the rotation itself of the storm. So some issues as you're looking at MESH, especially when you're looking at some of the higher values. And I showed this before, but we're just looking at that storm when we got the 4.5-inch report. You can see how sheared it is and also the presence of that bounded weak echo region. So based on some of the limitations we know about MESH, we would expect that maybe it wouldn't be performing the best at this time. So this is a graph of the LSRs that we received, but then overlaid with MESH as well in gray. And you can see the size is updating every 2 minutes associated with MRMS. And you can see overall with these larger sizes, MESH is really underestimating. It does capture the idea of some giant hail, but perhaps not at the right time. And then while it does stay above about 1.75 to 2 inches most of its life cycle, still seems quite a bit too low when you compare it to some of these giant hail reports that we were getting into the office. So does help you with the idea that the storm is severe, but isn't capturing some of the larger sizes that we were able to see in real time. So one of the things that we do use in real time is the 4-inch hail checklist. This is something that we fill out before we are expecting severe hail. And you can see at the top, once you fill out some of your temperature heights, it asks whether you're expecting well-organized storms or perhaps not as well-organized storms. And when you're looking at either your initial updraft developing or lesser organized storms, single cell, multi-cell without rotation, that's where the Donovan method would come in very handy. Just a lookup table based on your melting level, what 50 dBz height you should be looking for severe hail. But again, that's only going to tell you if you're expecting severe hail or not. It's not going to get you into those larger sizes that you would expect once you have a rotating storm. So these are the things that we look at when we're differentiating supercells that would be capable of producing significant hail versus those that might be capable of producing giant hail. And I have a link to this at the end if this isn't something that your office currently uses. But just pulling some of the data out and comparing them side by side. For giant hail, we'd be expecting a very well-organized supercell with rotational velocity of 40 to 60 knots, a storm top divergence of 120 to 180 knots. And these are subject to seasonal variability, but since a lot of these storms were occurring in the spring to summer in the Central Plains, we did look at these heights for this case. But a 50 dBz height greater than 45,000 feet and a 60 dBz height greater than 35,000 feet. And then for your significant hail, you'd be still looking for a supercell mode in this case, but perhaps a little lower rotational velocity of 30 to 45 knots, a lower storm top divergence of 80 to 120 knots, and then slightly lower 50 and 60 dBz heights as well. So when we look at all of these criteria for the storms, we looked at every single radar time frame from both EAX and TWX. And what we come up with based on that giant hail checklist is that pretty much the entire period from 1830 to 2100 UTC, we were looking at the potential for giant hail based on the storm structure. And this really captures those giant hail reports a lot better and gives you an idea of what that storm was capable of producing and perhaps just was not observed in real time. So overall, this is giving you a better picture of how to anticipate and what might be happening in between reports. And you do see that little transition zone around 1948 UTC. That was when there was a pretty significant updraft merger, and we did see a little weakening in the rotation of that supercell. But overall, for the majority of that time, the supercell was capable of producing giant hail. So a quick summary of just some of the hail data. We had a long-lived supercell with multiple updraft mergers that produced giant hail on at least 3 occasions throughout our CWA. Those giant hail reports all came from a well-structured supercell with a rotational velocity of at least 45 knots, a storm cup divergence of at least 150 knots and quite a bit greater in some cases, and 60 dBz all above 35,000 feet. Mesh did capture the swath of significant hail, but did miss those larger sizes. So maybe a good tool to use for situational awareness and to let you know that that storm is capable of producing hail throughout its life cycle. But the giant hail checklist really better captured all of those giant hail reports and the potential for that storm to produce giant hail. And then before I wrap up, I'll really quickly talk about the DSS events that we were supporting. So there was one scheduled outdoor event in Perry, Kansas. If you're not familiar where that is east of Topeka, kind of northwest of Lawrence. They were contacted via phone in the morning as requested. And then when the staff asked if they wanted follow-up calls for severe weather, the EM just said he would be monitoring and would contact us if he needed anything. So not a huge workload there. But then a bunch of other events did end up calling and letting us know that they had outdoor events going on during the day. They saw the storms developing and then wanted additional support. So there are several others that weren't on the calendar but did reach out and want support throughout the event. And NWS chat was mainly used throughout the event. This is something that we're pushing on our mesoanalysis team and also through the OPG, that this is a really great tool to provide mesoscale updates. And this is something that was done both prior to convective initiation around 16Z, during deep convective initiation when it was realized that the storm was developing quite a bit quicker, that the event was starting a little earlier than was anticipated. So it was a good way to provide those updates to the media and EMs. And then it was used throughout the event to help communicate the increasing potential for giant hail. And this was something that I sent out to the forecasters. I borrowed from Jared Layton at Pleasant Hill, and it's just something that I think is a really good tool to help collect information after the event. Then you can collect everyone's experiences and incorporate that into any event review, or especially as management, just to make sure that everything went well. If you have new employees or if there are equipment problems or anything like that, to be able to follow up with it later. So this was sent out to all of the operational staff working the event. I got 4 responses out of the 6 that were working, which is pretty good. And it just kind of goes over, how did internal and external communication go? Did you anticipate the hazards ahead of time? Were there any challenges meteorologically? What was your overall satisfaction with how the event went? And you can also send this out to people working prior to the event, especially if they followed up afterwards to see how their forecast worked out. So that is all that I have. I'm going to leave these up just in case you're interested in some of the resources that I showed here. We've got the giant hail checklist first, which should be shareable on Google Drive. The GLM archive that's available through UMD, and then I wrote up some instructions that Dale from WDTD gave me for incorporating those into a West case if you're interested. And then also the forecaster survey, I've copied it over to a more generic format if that's something you're interested in using in the future. So that is all that I have, and I will take any questions.